So from the previous videos or previous study, we have able to understand that Arrhenius theory and Ostwald's dilution law can be only applied, can be applicable to weak electrolytes, okay? Weak electrolytes in which reversible reactions is observed, okay? So here, as for example, ammonium hydroxide, that is a weak base and weak acid, acetic acid, okay? They actually exhibit the reversible reactions, in which there will be equilibrium will going to exist between the unionized molecule and ions, okay? So there will be a equilibrium. That means there are the the forward reaction rate equal to the backward reaction rate. So at a point, that means at equilibrium point, the forward reaction rate of this reaction will become equal to the backward reaction rates, okay? So here in this case says we can apply Arrhenius theory or Ostwald dilution law. So what about strong electrolytes? Actually we cannot use this concept because according to Arrhenius theory, what there must be, oh, remember this point, okay? There must be an equilibrium, okay? There must be a equilibrium between the unionized molecules and ions, okay? Understand? But here in case of strong electrolytes, they will completely dissociated into their ions. Let's suppose, for example, HCl or sodium chloride, okay? In case of sodium chloride, they will completely dissociated into their ions, and in case of HCl also they will completely dissociated into their ions, okay? So that means this is an unidimensional or unidirectional reactions. There will be no any backward reaction. So if there is no any backward reaction, so we cannot write the we cannot get the equilibrium, because equilibrium is only coming from where? From reversible reactions, okay? So we don't have that that reversibility. So we cannot use the Arrhenius law or Ostwald dilution law in case of sodium, or that means strong electrolytes, okay? So why actually actually this strong electrolyte will not going to show the backward reactions like this, okay? The main reason is here that in case of weak electrolyte, it's actually actually the rate of formation of the ions, that means the dissociation process from the unionized molecule to ionized, that means ions, will be actually a slow process, okay? If the process of this forward rate is slow, then what will going to happen? This ion have some time to react with each other and to get back to their unionized molecules, okay? That means the backward reaction, there are some possibilities to uh, you know there actually they have the possibility to show the or exhibits the backward reactions, okay? But in this case, the rate of the actually the dissociation process is very fast. That means the rate of the forward reaction is very fast, okay? So that's why the ions will not going to get any time to combine with each other to form back that unionized molecules, okay? Understands? Okay, so that's why we cannot use the Arrhenius law or Arrhenius theory and Ostwald dilution law in case of strong electrolytes, okay? Again, also we can understand this this point, that means why we cannot use the Arrhenius theory or Ostwald dilution law for strong electrolytes, okay? And the concept is actually coming from the experimental value, uh, which is actually XRD, or we can say X-ray crystallography, okay? X-ray crystallography data, crystallography, okay, data. So what they did actually, uh, the scientists actually they carried out the external crystallography and XRD of some strong electrolytes. So what is XRD and X-ray crystallography? Actually this XRD or X-ray crystallography, so XRD actually X-ray diffraction study, okay? So this XRD or the X-ray crystallography are actually characterization tools or analytical tools by using which we can get the information about the structure of an strong electrolytes. Okay, that means the not a strong electrolyte, for some crystal. Okay, some crystal that is actually their bone angle and bone length, like that. Okay, so we can get the information, actually structural information of a crystal. So since actually what they did, actually they try to carry out this X-ray crystallography or XRD for some strong electrolytes like sodium chloride, sodium fluoride, potassium fluoride. Okay, like potassium chloride. Okay, sodium hydroxide. Okay, sodium sulfide. So actually they carried out their the XRD analysis of this compound, and they found a very interesting result. Okay, this is a very interesting and a very important result. Okay, so and the result is that, and they found that, actually they found that the crystal lattice, okay, the crystal lattice in these substances, actually in this substance some crystal lattice will be there now, because they are in crystal form, consist exclusively of ions. So this point is very important. So that means only ions are there. Okay, that means that crystal lattice, that means the crystal lattice, or the what crystal lattice is, what it is coming from solid state. Okay, that means the solid state of sodium chloride. Okay, or you can say the crystal of the sodium chloride is only formed exclusively of their ions. That means sodium positive and Cl negative. Okay, so there will be no any molecules. Understand? So here, that means let's suppose this is your sodium positive and Cl negative, and here many chloride will be Cl negative, Cl negative, Cl negative, Cl negative. Okay, so 6, 1 2 3 4 5 6 6 chloride, and we're going to surround this sodium positive. Okay, and again similarly there, sodium positive, sodium positive, sodium positive. Okay, here also sodium positive. So again here sodium alternative. Okay, alternative, there will be some alternatives, chloride negative. So there will be what, they will going to form that crystal, and that crystal is only consist of what, ions, purely ions, sodium positive. Okay, ions, there will be no any molecules. So this is very very important result. Okay, this result from that crystal, that crystallography data or X-ray crystallography. So that means there are no any molecules. Hence in such cases, that means in case of this strong electrolytes, in case of this strong electrolyte, there are no any question of equilibrium, because if equilibrium means what, equilibrium is only exists between unionized, ionized, unionized molecule and ions. Okay, so that means ions of that ionized molecules. But since there are no any molecules will going to exist in the crystal, then how can we write unionized molecules? We cannot write unionized molecules. Okay, understand, no? So we cannot write unionized molecule here. Understand? So if there are no any ionized molecule, then how can we write these reactions? We cannot write these reactions. Okay, so even we cannot think about this. That's why we cannot use the Arrhenius theory to understand this strong electrolyte. So now coming to the nature of the bond of strong electrolytes, or strong acids, or strong bases. Okay, strong electrolytes. Okay, so since we able to know that the nature of actually the strong electrolytes is actually consist of what, consist of purely ions. Okay, let's suppose consider sodium chloride. Actually there will be many, actually this sodium positive will be surrounded by total 6 chloride, and this chloride will be surrounded by 6 sodium positive ion. Okay, but just for simplicity, or just for to understand only one bond, we are just writing sodium positive and chloride negative. Okay, so here just concentrate on this bond. So if you see this bone, or then if you want to study about this bond, then you have to know about this composing materials or composing atoms. Or but here these are not in atomic form, they are in ionic forms. So again we know from the Coulomb's theory that if some ions are there, opposite ions are opposite charges, so there will be some attraction, and the force of attraction, that means the magnitude of the force which are exerted between these two charges can be actually calculated by using the relation F is equal to q1 q2 4 pi epsilon naught r square. Okay, so here actually the r is the distance between these two charges. Okay, and q1 represent the charge of sodium positive, and q2 represent the opposite charge, that means your chloride negative. Okay, and this force is actually what? This force is actually your inter-ionic force. This force is known as inter-ionic force. That means the force between the two ions. That's why inter-ionic. Okay, between the two ions, inter. Okay, so here if you notice this this relation, then we have observed that actually this q1 and q2 are constant for a particular uh, you know uh, crystal. Okay, this is constant because sodium chloride, it is always +1, it is always -1, and 4 pi is also a constant. So that means F is actually related, or F is actually this interionic uh, you know this interionic force will going to actually depends upon mainly two variables. One is epsilon naught and other is your r. Actually this is epsilon, no, epsilon, and this is F is inversely proportional to the r square. Okay, so that means here this epsilon is actually it will going to vary with different medium. If you put this sodium chloride in water, then this will be different. If you put this sodium chloride in ethanol or other organic solvent, then it will be also different. Okay, because actually this dielectric, actually this epsilon represent what? Dielectric constant. Dielectric constant for different substances are different. Okay, and this r is actually depends upon the distance between these two charges, no? So if you put these ions in different solvent, then also this r will going to be different. Okay, we're going to discuss this one. Okay, this point. So now let us discuss, let us suppose we are going to put this sodium chloride in water. Okay, so in water, always remember that the epsilon naught is equal to almost 80. So what is the meaning of this one? That the dielectric constant of water is 80 times higher than the air. Okay, so if you if you add sodium chloride in water, then what will going to happen? That because this epsilon naught is very high, na? 80, almost 80. So if you put here 80, then the interionic force will be low. That means the force which will going to bind these two are low. As a result, they will going to break, this bond will going to break, and they will going to form ions. Understands? So actually this will going to depends upon the this dielectric constant. That means the how fast they will going to dissolve, or how many ions will going to be produced from that electrolyte will actually depends upon the solvent also. Okay, so coming to the theory which is given by DY, actually Peter DY and E. Haeckel, okay, in 1923, okay, for strong electrolytes. Actually, we can explain the nature of strong electrolyte in any solvent by using this theory. Okay, so according to this theory, actually they suggest that actually according to them, the strong electrolyte, in case of strong electrolytes which exist, actually strong electrolyte will going to exist as what? As ions, na? They will going to exist as ion even in solid state, state. Okay, so according to them, strong electrolyte, all strong electrolyte, okay, so which are actually exist as ions even in solid state completely ionized. So they will going to completely ionized in completely ionized in solution at any concentration. Solution means solution of with any solvent. Okay, solution at any concentration. So this is the theory actually. So according to Debye and Haeckel, all the strong electrolyte which are actually exist as an ion even in solid state. This is actually coming from where? This is coming from the XRD data. Okay, so in solid state completely ionized, so they will going to completely ionized. Okay, so please remember this point, ionized, not dissociated. Okay, completely ionized in solution at any sort concentrations. Okay, so let us discuss this point or this theory by using some example. Okay, so let's suppose we have some strong electrolyte. Let's suppose this is your strong electrolyte. Okay, so they will be in ionic form in even in their solid state. Okay, so let's suppose it is in their solid state, and here this is the distance between these two, and then we already know that the F, that means interionic force of attraction, will be Q1 by Q2 4 pi epsilon naught R square. So we already know this one. Okay, so now let us consider some conditions. So first condition, let's suppose the dielectric constant is high. That means let's suppose water. Okay, in case of water it is very high. Okay, it is almost 80. Okay, so if dielectric constant of that medium or that solvent is high, then what is going to happen? So if the concentration of the solution is low, then the F is very low. So F is very low. So if it is low, then they will going to completely ionize. They are already ionized, but they will completely dissociate it. Okay, so as a result, in this case, ionized as well as dissociated, completely dissociated. Okay, dissociated into their ions. Why completely dissociated? Completely dissociated means what? They will going to form corresponding ions. That means they will going to be like this. Okay, if you add XY in a dilute, let's suppose water. What amount of water is very high, that means it is a dilute solution. Okay, so if you add a little amount of XY, then that XY will going to form only ions. Okay, that means the strong electrolyte which is added to that water, excess amount of water, will completely dissociate into their ions. Okay, in case of if the this epsilon is high, that means the dielectric constant is high for this medium, that means water, and the concentration is low. Understand? Because of that force. Clear? That interionic force. This is the first condition, let's suppose. Now consider second cases. In the second case, let's consider epsilon naught is low. Let's suppose ethanol. Okay, ethanol. So in comparison to the water, ethanol has very low dielectric constants. And let's suppose the concentration is low. So even though the concentration is low, since the epsilon naught is what? Small, then what about this F? This is small. Okay, even though the concentration is low, actually concentration low means what? Actually when you decrease the concentration, actually the R will going to increase. Okay, the main point is that. So if you decrease the concentration, that means if you dilute the system, that R will going to increase. Okay, so even though the R is increased, but this epsilon naught is very small. Okay, then your F will not be so small. So that means F is low but not so low. Okay, that's why in this case, what will going to happen? The ionized, completely ionized, no problem, ionized, completely ionized. Ionized means what? They are in ionic form. We already know that solids are in ionic form. No? The constituents are what? Ions. So they are already in ionic form, but not completely dissociated. Okay, but not completely completely dissociated into their ions. Understand? So some of them will going to be remain as what? Remain as doublet. So let's suppose you add x y, no? So it will be like x positive y negative. So they are like this doublet. They will be associated. They will be, you know, they will be like a pair of ions. Okay, and such pair of ion is known as actually ionic doublet. So remember this point. Okay, remember these terms: ionic doublets. Clear? So this is actually the second part. This is second case A. Okay, second case B, same case. Okay, let's similarly, let's suppose your epsilon naught is high. Suppose this is water. Again, you are taking water, but concentration is very high. Okay, if the concentration is very high, then the R is what? R is very small. R is very small. So even in such cases also, you are going to get the same conditions, because in such cases also, because concentration is high, means R is very small, so F is higher. Okay, so that's why they will be in doublet form, that is ionic doublet. Understand? So here it is actually ethanol in case of this this second A. Even if this one is low, no doubt this one is low, even if this one or concentration, if the concentration is high, then also it will be like this one. Okay, understand? So these are actually the conditions or some cases by using which we can understand the Debye-Hückel theory. So actually according to Debye-Hückel theory, they are completely ionized. So here you see in the first case they are completely ionized, but not they are also dissociated completely. But in the second cases, there are mainly two cases, no? Second A and B. The completely ionized, they are completely ionized but not completely dissociated. What is the meaning of ionized? Why completely ionized? Because they are in the form of ion. Okay, so do you understand this point? Why they are completely ionized? Because we already know that the sodium positive and chloride are what? They are in ionic form, no? In solid state also. Their constituents are what? Ions. So they are, that's why they are completely ionized. Okay, but they are not dissociated. Dissociated means they are not far from each other. That means they are not dissociated into their ions. That means, let's suppose this is sodium chloride. Okay, in the crystal. So this is ionized, but this is ionized, not dissociated. Okay, so when we add this in water, then they will going to far from each other. Okay, and they are going to be dissociated because the interionic force will be what? Less. So they will be going to, they can move freely. The sodium can move freely and chloride can move freely. So they are dissociated. Understand? Understand this point? No? So now we're going to discuss about the Arrhenius. Actually, he actually used some concept to calculate the alpha. Okay. So coming to the Arrhenius concept of increment of conductivity on dilution. So according to him, if we dilute a system, then the conductivity will going to increase due to the increment of degree of ionizations. Okay, so according to him, the conductivity, this is actually degree of ionization. Okay, ionization. Okay. So according to him, the conductivity of a system of a electrolytes will going to increase on dilation because of the increment of the degree of ionizations. Okay, so according to him, this concept is correct, but we cannot use this concept for strong electrolytes. Why? But this can be okay, this is true for weak electrolyte, but strong electrolyte, no, it is not right. This is incorrect. Okay, this is wrong. Why? Because we already in actually according to Debye-Hückel theory, we know that all the strong electrolytes, in case of all strong electrolytes, they are completely ionized in all concentrations regardless of their solvent. Okay, so that means alpha is equal to 1 for all the strong electrolyte. So that means they are completely ionized. Alpha is, that means degree of ionization is 1, that means 100%. Okay, they are completely ionized. Strong electrolytes. Okay, so for strong electrolytes, the degree of ionization is 100% according to Debye-Hückel theory. So we cannot use this one. So that means degree of on dilution, it will not going to increase now. So according to them, what? According to Arrhenius, if you dilute the system, then this will going to increase. Okay, this will going to increase, but here in case of strong electrolyte this is already 100%. Then how will going to increase from 100%? It will not going to increase from 100%, na? So we cannot use this concept in case of strong electrolytes. So then what is the concept, or what concept we can use to justify the increment of conductivity of on dilations in case of strong electrolytes? Because we have observed that even in case of strong electrolyte, if you dilute, let's suppose this is your strong electrolyte, okay, concentrated solution. Let's suppose this is your concentrated solution of strong electrolyte, okay. So strong electrolyte, but here it is concentrated, okay. So if you dilute this strong electrolyte having higher concentration, so if you dilute this one, then also you will observe the increment of conductivity. That it may be lambda m or kappa, anything, okay, it is increased. But why the increment is occur? So according to actually Debye-Haeckel theory, this is not because of the ionization, because they are already ionized, completely ionized, okay, but because of actually interionic attractions, because the interionic attraction will going to be lower if you add more and more solvent to that solution, because f is depends upon what, q1 q2 4 pi epsilon naught by r square. So but here all the parts are what, constant for a particular electrolyte, because epsilon naught is also constant for that particular solution, because epsilon is depends upon what, solvent, but solvent is same, na, so it will be constant, but it will depends upon what, r. That means if you dilute the the system, that means the concentrated solution of strong electrolyte, then the distance between the ions will going to increase, the r will going to increase, okay, r will going to increase. As a result, f will going to decrease. If this is going to decrease, then what, if this is going to decrease, then more and more ions, more and more strong electrolyte will going to dissociate it into the ions, not ionize, okay. Ionize is, they are only ionized already, they are completely ionized, but not dissociated, na? The undissociated, that means the ionic doublet, they are in which form? In concentrated form. We already know that they are in doublet form, okay, and this doublet will going to dissociate it into more freely movable ions. That means, understood, na? If the free movable ions will be, the number of free movable ions will going to increase, then conductivity also will going to increase. That is the reason, okay, that is the reason of the increment of conductivity on dilution for strong electrolyte. Understand? So now coming to the quantitative idea of actually here you see this is your lambda m. Lambda m represent actually what, the molar ionic conductance. Actually there are some effects in the strong electrolyte, in case of strong electrolytes, which will going to decrease the molar ionic conductance. Let us discuss about them, okay. So first of all, before the discussion of that this decrease of this molar ionic conductance, so we have to know some some basic concepts. So let us discuss about them. So first of all, we know that when we add that strong electrolyte in a solvent, then they will going to dissociate it into their ions, okay. So let's suppose this is positive ion, so there are many positive ion will there, there are many positive ion will there, many negative ion will be there, so okay. So at that condition, that room temperature, let's suppose that room temperature, there will be some energy, thermal energy, which is represented by K into capital T, okay. This represent what, thermal energy. So at the thermal energy, because of the thermal energy, these ions can move, they try to move what, randomly, okay. So this is because of the thermal energy. And also additionally, we know that there will be some attraction force between the opposite charges or opposite ions, okay. So because of that attraction, they will going to attract the, let's suppose this positive ion will going to attract the negative charges, okay, and they try to form a sphere, okay. This negative charge will try to surround this positive ions, okay. So let's suppose this Coulombic force will going to attract this one, so Suppose this chloride this negative will be there and this negative will be there. Okay, so because of the thermal motion they try to move now. So suppose they will moving like this direction, and this negative will going to move this direction, this move will going to move this direction. Okay, so in their path they will going to find some positive ions. So when they find the positive ion, there will be some, let's suppose at this position they are coming, this ion will go from here to, let's suppose this one. Okay, so at this point there will be some interaction, let's suppose. Okay, and this will again go to this part, so there will be some interaction. Okay, some ions, negative ion. So what will going to happen, they will going to form a sphere. So if you zoom this one, it will be like this. Okay, so let's suppose this is your beaker. So here this is your positive charge. Okay, this is your negative, this is your negative, main thing. Okay, negative, negative, this is positive, like that. Okay, so let's suppose this is going this way. Okay, this is going to move this way. Okay, this is also moving this way, this is going to, this is actually moving this way, this negative is moving this direction, let's suppose. So when this is moving to this direction, then what will going to happen, they will going to find some positive ion. So let's suppose at this position, so they are moving from here to here. Okay, at this position they interact with each other. Okay, so there will be some coulombic force. Because of that coulombic force, it will not go further this direction. Okay, it will going to remain at this position. Okay, so similarly this will going to remain at this position, and there will be some coulombic force, and this one will going to remain this position, so there will be a coulombic force. Okay, and this one will going to remain this position, that means there will be some coulombic force. Okay, so what will going to happen, they will going to form a sphere. Okay, and this sphere is actually this sphere is actually a ionic atmosphere, and this atmosphere is known as what, ionic atmosphere, spherical ionic atmosphere. Okay, atmosphere, PCR. Okay, so atmosphere. So because of this ionic atmosphere, there will be some decrease of molar ionic conductance if we apply some electrodes. Okay, and try to calculate their conductivity. Okay, so let's discuss about them. Mainly, actually there are three types of effects actually observed in an electrolytic solution, mainly strong electrolytic solution. Okay, first one is your asymmetry effect. Okay, asymmetry effect. Second one is your electrophoretic effect, and third one is your viscous effect. Okay, and this all three will going to impact on, they will going to exhibit some impact on the magnitude of lambda m. So we're going to discuss about this. Okay, so first let us discuss about the first one, which is your asymmetry effect. So here let's consider this one is your ionic atmosphere, symmetrical ionic atmosphere. Okay, so this ionic atmosphere is already, we know that this is formed because of two factors. One is your coulombic interaction and other is your thermal collision, and they will going to form a symmetric ionic atmosphere. Okay, so in that strong electrolyte solution. Okay, so now let us consider we just apply, or we just insert two electrodes in that electrolytic solution and apply some potential gradients. Let's suppose this is your positive, okay, and this is your negative electrodes. So as a result of this one, what will going to happen, this symmetry of this ionic atmosphere will going to disturbed by this this field. So here the negative charge will going to attracted by this positive electrode, and they will going to move this direction. They will going to move this direction. Okay, these directions. Okay, so if they will going to move this direction, then what will going to happen, their symmetry, and actually this positive will going to move this direction because of this negative electrode. Okay, so because we applied this negative electrode here. Okay, so because of this movement, that means the movement which are actually what, different direction, no? Opposite direction, to the opposite direction, the symmetry of them will going to decrease. not decrease, the symmetry will going to be actually it is destroyed, okay, destroyed by this the applied electric field, okay. But here again you know that there will be some interaction, okay. So first of all, there this negative charge or this negative ion will going to move towards this direction because of what? Because of this applied potential. But here if you notice this part, then there will be somewhat interaction, Coulombic interaction, you see, there will be some Coulombic interaction between these negative ions and positive ions, okay. So they will going to what? They will going to decrease the movement of these positive ions towards the negative electrodes, okay. As a result, what? As a result, the molar ionic conductivity of this will going to decrease, and this is known as asymmetry effect. That means the decrease of this molar ionic conductivity is due to the asymmetric effect, because you see this is your symmetric what? The symmetric atmosphere, and because of this this asymmetric atmosphere, okay, because of this asymmetric atmosphere of the negative charge, that means the anion, and because of the interactions between the negative ions, which is your anions, with the cation, the movement of the cation will going to decrease, okay. As a result, the observed molar ionic conductivity will going to be decreased, understand. So this is actually known as this actually the drag on the central ions. This is actually central ion, okay. This is known as central ion, positive ion is it? So central ion is known as what? Asymmetry effect, okay. So because it is actually, it arises from what? A lack of symmetry in the atmosphere of a moving ions, so it is known as what? The asymmetry effect, understand. Now coming to the second effect, which is your electrophoretic effect, and this is a very interesting effect, okay. So here let's suppose this is your positive charge, okay, and this is your negative charge, okay. So here many water molecules is there, so we know that they are actually solvated. The positive ions are actually solvated by water, okay. So there will be some water, okay, like this, oxygen, hydrogen. So it will going to make a sphere, okay. So solvated ion. So similarly this negative ion is also surrounded by the positive. Is del is, that means is del positive now. So it will going to move, form a, this will going to form it what? This will going to form a sphere, okay. Okay, understand. So when we apply, let's suppose we apply here negative excuse me, negative potential at that electrode, and here positive, okay. So because of this applied potential, this negative charge try to go from here to here, okay. They try to move now, but here they will and also this positive will going to go towards the negative electrodes. So they will going to what? They will going to experience some they experience some environment. You see this water, actually this water will going to move along with this positive charge, okay, because this positive will going to move this way, and this water will also going to move along with this positive, and here negative charge is moving this way, and some water molecule will going to again move with this negative one. So there will be what? This opposite direction, this water molecule is moving this direction, and this water molecule is moving this direction. Because of that, what will going to happen? They will going to experience some opposite flow. They will going to experience some opposite flow of this movement of water molecules, and this actually effect will going to what? This counter current actually slow down the ions in the same way as counter current in a stream slow down a swimmer, okay, like this. And this effect is known as electrophoretic effects, understand. And then next, actually third point is your viscous effect. So actually this point is not so hard, this is very simple effect. So actually the movement of the ions, it actually depends upon the viscosity of the medium. That means if the viscosity of the medium is high, then obviously we know that it will be hard for the ions to move to that electrode. So it is that means the mobility is directly related to the viscosity coefficient. Okay, that means if the viscosity of that medium is high, then so it is inversely. Okay, if the viscosity is high, then the conductivity is going to decrease. In 1926, Debye and Haeckel and Onsager actually they derive an equation. Okay, actually this equation, and actually the derivation is not in your syllabus, so just try to remember this equation. Okay, so they derive this equation and try to, and by using this equation, actually this relation, we can calculate the molar ionic conductivity of a strong electrolyte. Okay, so here if you notice this equation that you find it, this is actually just lambda m. This is your molar ionic conductance or molar ionic conductivity. This is your molar ionic conductivity at infinite dilations. And actually this first part, actually this is coming from the electrophoretic effects. Okay, and here this is actually coming from the viscosity. Okay, viscous effect. Okay, and this epsilon r is actually your dielectric constant, and this is your coefficient of viscosity of that medium, and here c represent the concentration of the solution. Okay, that means the electrolytic solutions. So the first part is mainly coming from the electrophoretic effect, and the second part of this, actually this part is coming from your asymmetry effect. Okay, so we can for a given for a given solution, and at constant temperature, we can write this equation like this one. Okay, lambda m is equal to lambda m naught minus a actually represent this part. Okay, and b lambda, actually b represent this part. Okay, actually this part will become constant at constant temperature for a given solution. Okay, this part and this part. Okay, so ab and root over c. So and for actually 25 degrees, if the temperature is 25 degrees Celsius, and then this a become 60.2 for water. Okay, for water, if the solution is made in water, that means the solvent is water. Okay, then a becomes 60.2 and b become 0.229. Okay, at 25 degrees Celsius. So it is actually for at 25 degrees Celsius for water. So water is what? Solvent. So water is your solvent. Okay, so we can write lambda m naught is minus this constant lambda m naught root over c. So it is actually like, it is an equation of straight line, right? Y is equal to mx plus c, mx plus c. So if you notice here, so wait 1 minute. Okay, so this is your actually graph. Okay, so we can actually they carried out they actually they try to calculate the molar ionic conductance for different um, different strong electrolytes. In your you can see it from the right hand part of this PDF. Here the figure 13, some graphs are there, no? So that first is what? Hydrochloric acid, potassium chloride, silver chloride, and silver nitrate. Okay, so it is actually the in x-axis they draw what? Molar conductance. Okay, so this is your lambda m, and here the concentration. So what is our equation? Lambda m is equal to lambda m naught minus some constant will be there, no? So this is your, so this part is your 60.2 plus 0.229 lambda m naught root over c. Okay, so here it is actually y is equal to, actually this part, actually this is actually constant part minus mx. So x is equal to this one. Okay, but here this is minus na, so we will get negative slope. Okay, so here this equation represent a straight line. So if you use some strong electrolyte at HCl or potassium chloride, okay, so if they follow this equation, so if you actually try to calculate their their lambda m value for defined concentration, that means defined concentration, so you can get some value, na? So if you get that value, So you have lambda m value for different concentration. So you can plot this data, no? So you can, or even you can lambda root over concentration. So you can plot this graph. So if the graph is a straight line, then that means that this equation is correct, or this equation is valid, okay, or this equation is a true equation. Or you can use this equation for other strong electrolyte also. So they did, for many strong electrolytes as HCl, potassium chloride, silver nitrate, silver, or sodium nitrate. So they found some straight lines like this, okay. So which indicate this is true. That means this equation is true for strong electrolytes. So next effect is your Debye Falkenhagen effect, okay. So actually what they did, they calculate the molar ionic conductance by applying alternative current, okay. But here they apply what? Alternative current. And try to calculate the conductivity of that solution, okay. So they found that the conductivity is actually increased, or it is actually they found higher conductivity value in comparison to the conductivity value which is calculated from that direct DC. That means just this direct potential, that is that battery, okay, negative and positive. So if you apply here instead of AC, if you apply DC, then let's suppose you will get lambda m1, okay, lambda m DC, okay. So that value is actually smaller than this value. So why actually the value is smaller? The main reason of this is that they found the reason as the uh, ionic sphere, okay. So actually the ionic atmosphere, in case of this when we apply DC, then this ionic atmosphere become what? Asymmetric, and because of that asymmetric effect, the molar conductance will going to decrease. But here, in case if you apply AC current, that means alternative current instead of DC, then what will going to happen? This 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 sphere will going to remain same. That means the asymmetric effect, we can totally omit the asymmetry effect in the calculation of lambda m. That means this effect is completely removed. We can remove this asymmetry effect by using alternative current, okay, instead of this direct current, okay. So this is actually the main concept of, or the main effect which is observed by the Debye Falkenhagen, okay. Again, they also observed that if we applied, if actually they applied different frequencies of alternative current, and they found that if the frequency is high, then the conductivity also is high. That means conductivity of that solution, that means strong electrolyte, conductivity of the strong electrolyte is directly proportional to the applied frequency, okay. That means the frequency of the alternative current, understand. And actually this process is known as the removal of the asymmetry effect due to the presence of that AC, and also the higher frequency, when we apply higher frequency, the conductivity will going to increase, na? So this increment of this conductivity due to the applications of higher frequency is actually known as dispersion of conductance. So this effect is known as dispersion of conductance, okay, understand. So try to remember this, these terms, okay. Sometime maybe in the exam they may ask you what is dispersion of conductance, so you have to write these things, okay. So I hope you understand this effect. So always mainly there are 2 points in this effect, okay. The first point is that the asymmetric effect is totally removed. We can remove the asymmetry effect completely by applying AC instead of DC. And second is if we apply higher frequency, then the conductivity of that solution will going to increase, okay. And this effect is known as what? Dispersion of conductance. The last effect is Wien effect, and this effect is introduced by Wien well before the all the theories of strong electrolytes, and he actually applied almost actually 20,000 you know volt per centimeter potential gradient. That means he applied a very huge amount of DC potential gradient to calculate the molar ionic conductance or the conductivity value. So when we applied actually this huge amount of potential gradient, then actually the ions, the, let's suppose the positive ion or the negative ions will going to have, they have a very high speed. Okay, almost 100 centimeter per second. Okay, so it is actually this is a very high speed. Okay, 100 meter per centimeter, actually the unit is centimeter per second. Okay, so this is a very high speed. So since the speed of these ions, that means the positive and the negative ions are very high, so they don't have enough time to form the ionic atmosphere. So as a result, the asymmetry effect will be absent. Okay, in this case. And additionally, also there will be no any time for for the formation of the solvated ions. So that's why also the electrophoretic effect is also absent. So that means we will get a higher value of conductivity value, that means molar conductance value, if we apply a very high potential gradient to calculate the lambda m value. Okay, so uh, that means we can say that the conductance of a strong electrolytes in aqueous solution increases to a certain limiting value with the increase in potential gradient applied. Okay, if we apply a very high potential gradient, then we can get a very a high value of lambda m, and it will going to increase to a certain limiting value. That means if you increase the potential gradient, then will the lambda m value also going to increase to a certain value. Okay, and this observation has been actually verified by Wine, and well before the development of the theory of strong electrolytes. And this theory is known as, actually this effect is also known as Wine effect. So this is a very simple effect. Okay, so the main points are, in Wine effect we observe the Wine effect in case of high potential gradient. That means when we apply high potential gradient, okay, then only we can get Wine effects. Okay, and if we apply high potential gradient, then asymmetry effect as well as the electrophoretic effect will not going to be there. Okay, these two effects are missing. Okay, that's why the conductivity value is higher. Okay, hope you understand the Wine effect. So in the next class we're going to discuss about the electrochemical cells. Mainly two types of cells are there, no? Electrochemical cells and electrolytic cells. So we're going to discuss in details about the cells and the chemistry related to that cells. Okay, or the electrochemistry of cells.